Okay, in this session we are going to discuss about the electric field intensity due to an infinite long charge conductor by using Gauss theorem. Okay, therefore let's initially draw a charged conductor, and this is our conductor. It is having positive charge on it, and now we are taking a finite long conductor. Then in order to find out the electric field intensity, we are using Gauss theorem. For using Gauss theorem, we have to consider a closed surface, and in this case we are taking a closed surface in the form of a cylinder. We are taking a closed surface in the form of a cylinder around the charged conductor. And as we all know, cylinder will have two flat surface and one curved surface. And after this, I am marking the direction of area vector on the two flat surface and the curved surface. Area vector is a vector which is directed perpendicular to the area. Therefore, on the upper curved surface, the direction of area vector will be like this. Let me mark it as ds. And on the lower curved surface, the direction of area vector is like this. Since area is like this, area vector will be vector perpendicular to area. And over here also I could mark the area vector. It will be directed upwards, ds. On this surface also the area vector is directed downwards. Then on the curved surface, assume that this is the curved surface, then at this point the area vector will be directed outwards. At this point the area vector will be directed outwards like this. Therefore at this point I am marking the area vector like this, ds. And over here the area vector is like this. Therefore we have marked the direction of area vector at different points. Now we are going to mark the direction of electric field intensity. As you all know, the direction of electric field intensity will be in the direction of electrostatic force experienced by a positive charge, unit positive charge. And in order to find out the electric field intensity over here, assume that we are having a positive charge over here. What will this conductor do? Since the conductor is positively charged, if I am placing a positive charge over here, there will be force in this direction. Clear? Therefore, the electric field intensity on the upper surface, it is like this. And on this upper surface, the electric field intensity, if I am placing a positive charge over here, it will experience a force in this direction. Therefore the electric field intensity over here, it is like this. And over here also, if you are analyzing the electrostatic force experienced by a unit positive charge, it will be like this. Therefore on the curved surface the electric field intensity is like this, and on this curved surface also electric field intensity is like this. At the bottom flat surface, assume that we are having a positive charge over here, it will experience a repulsive force like this. Therefore this is the direction of electric field intensity, and at this point also we will have electric field intensity like this. Now we have marked the direction of area vectors and electric field intensities on the Gaussian surface. Now we could use the Gauss theorem. In order to use the Gauss theorem, what is Gauss theorem? Gauss's theorem is saying phi is equal to integral of E dot ds, that is equal to q enclosed by epsilon 0. The total electric flux enclosed by a closed surface is 1 pi epsilon 0 times charge enclosed by the surface. And in this derivation, or in this theorem, we will use only this portion of the theorem. Since we require only electric field intensity, I will be using only this part of the Gauss theorem. Then initially let me write on flat surface. We are writing on flat surface. Let's analyze the situation on the flat surface. At the upper flat surface and lower flat surface, you can clearly see E is perpendicular to ds. Electric field intensity and area vector is perpendicular. Therefore, the angle between electric field intensity and area vector is 90 degree. Then what should be E dot ds on flat surface? On the flat surface, E dot ds will become E ds cos 90. What's the value of cos 90? Cos 0 is 1, cos 90 is 0, therefore it will become 0. On flat surface, E dot ds is 0. Then let me write on curved surface. We are analyzing the direction of electric field intensity and area vector on the curved surface. And on the curved surface, you could clearly see the electric field intensity is parallel to the area vector. Therefore, the angle in this case, it will be 0 degree. Then the value of E dot ds on the curved surface will become E ds cos 0. Since the value of cos 0 is 1, we could write it will become E ds. Then, after writing these, I am rewriting the Gauss theorem over to this point. Gauss theorem is saying integral of E dot ds is equal to q enclosed by epsilon 0. I am expanding it, integral curved E dot ds. I am using this as curved E dot ds plus, since there is two flat surface, 2 integral flat, this is flat E dot ds, that is equal to q enclosed by epsilon 0. Instead of integral of E dot ds, I am writing integral curved E dot ds plus 2 into integral flat E dot ds is equal to q enclosed by epsilon 0. Since we are considering a cylindrical Gaussian surface, and cylindrical Gaussian surface is having 2 flat surface and 1 curved surface. And after writing this, let's use these concepts over here. On the flat surface, E dot ds is 0. Therefore, flat surface E dot ds can be equated as 0. On the curved surface, E dot ds is EDS. Therefore, curved surface E dot ds can be written as EDS. Therefore, this equation is simplified into integral curved E ds, that is equal to q enclosed by epsilon 0. We could write the equation like this. Then the Gaussian surface is a cylindrical one, and the charge conductor is at the center of the Gaussian surface. That means the distance from this cylindrical point or the curved surface to the conductor is equal to this distance. Therefore, I could write, in this case, E is constant. We don't know the value of E, but E is constant. If E is constant, I could take that E out of the integration. Integral curved ds, that is equal to q enclosed by epsilon 0. I could write the equation like this. Then, what is curved surface integral of ds? For saying the curved surface integral of ds, let's assume that the cylinder is of length L and the radius of the cylinder is R. What is the curved surface area of a cylinder? Curved surface area of a cylinder will be perimeter into length. Therefore, instead of curved surface integral of ds, that is, I am writing this equation like this, that is E into, instead of curved surface integral of ds, I am writing circumference, that is 2 pi r into length. 2 pi rl is integral of curved surface integral of ds, that is equal to q enclosed by epsilon 0. Then we could clearly write E is equal to q enclosed by 2 pi r l epsilon 0. We are taking this 2 pi r l to this side and we could get an equation like this. Then from this equation, let's highlight this point or these two terms. What is q enclosed? It is the charge enclosed by the cylinder, that is the charge inside the cylinder. What is L? L is the length of the conductor inside the cylinder. As we know, there is a physical quantity which is called as linear charge density. What is linear charge density? It is the total charge divided by total length or charge per unit length. Therefore, we could write Q enclosed by L is the charge enclosed divided by the length of the conductor which is enclosing that charge. It will be linear charge density lambda. Therefore, I could write instead of Q enclosed by L, lambda. Thus, I could write the equation as E is equal to lambda by 2 pi epsilon 0 r. I could write r epsilon 0 or epsilon 0 r. And this is our equation for electric field intensity due to an infinite line charge. But you may have a confusion that we are using a finite line charge, and how can we say that this can be used for infinite line charge also? Because since we are representing the equation in linear charge density, in terms of linear charge density, it could be used for a finite conductor or an infinite conductor. Therefore, if the conductor is infinite long also, we could assume this equation. This is the electric field intensity due to an infinite line charge. E is electric field intensity. It is electric field intensity at a distance r from the straight conductor, where lambda is the linear charge density. Linear charge density is charge per unit length. Hope you have understood this derivation.